This lecture is about hypothesis testing in a special situation, namely when we have a linear regression model with several explanatory variables and we want to test a single restriction. And this test will be performed using something called the t-test. So the starting point is as follows. We have a linear regression model. We assume random sampling, and we also assume that the Gauss-Markov assumptions they hold. So our LRM looks like this. We have k beta parameters, k minus 1 explanatory variables from x2 through xk. We need the Gauss-Markov assumptions. First, we need the exogeneity so that we know that we can actually estimate the beta parameters using, for example, OLS and get unbiased estimates. But we also need the homoscedastic assumption because we want to be able to find the variance of the OLS estimates. Those are integral in all kinds of inference, of which hypothesis testing is one special case. As a concrete example, we can use this data set of 99 students where final is the result on a final exam. We use that as our y variable. SATV and SATM are the results on the SAT, the verbal and the math score. So those would be our x2 and x3. Our final explanatory variable here is this one, x4, the high school GPA. We will not use the pass one, that's just true if the student passed the final. So this is what our model looks like. The final result, the SATV, the SATM, and the GPA. And remember the interpretation of the beta parameters. For example, beta 2, the coefficient in front of SATV, is the derivative of the expected value of y given x with respect to x2. So beta 2 tells us the increase in the expected result on the final if the SATV score increases by 1 point if we keep the other variables fixed, that is, we keep x3 and x4 fixed. Because of the Gauss-Markov assumptions, we know that the best way to estimate the beta parameters is by using OLS. So let's do that. We do Gretel. We just go to model, ordinary least squares, final is our dependent variable, SATV, SATM, and GPA. And these are our estimates of the beta parameters. They all have the correct sign. It's positive. So a higher score on SATV results in a higher expected final score. Higher score on the SATM has a bigger effect on the expected final results, at least according to the estimates. And the GPA has a positive effect on the expected result on the final as well, although this coefficient is not really comparable to these other two, as this measures the effect on the expected final given an increase in the GPA by 1 unit. So our next step, if we want to do inference, we also have to make the normality assumption. So we have to assume that the error terms follow a normal distribution, and in this case the expected value must be 0 because of the exogeneity, and the variance must be sigma square and constant because of the homoscedastic errors. And remember that the Gauss-Markov assumption is pretty crucial to our results, while the assumption on the normal distribution is not. If the error terms are not normal, that's not going to affect our results very much. Especially if n is large, then the central limit theorem will work in our favor and we can relax this assumption of normality. So here is the hypothesis that we will consider. It's beta j equal to 0, where j is one of these numbers from 1 through k, and we will begin by looking at the t-value. So this is the hypothesis, beta j equal to 0. As a concrete example, let's look at beta 2 is equal to 0. If beta 2 is equal to 0, it means that x2 does not affect the expected result on the final exam when we keep x3 and x4 fixed. We often express this as saying that the marginal effect of the SATV score is 0. Or we say something like the SATV score has no effect on the final result. Such a statement is a statement that we would like to test. We want to see if this statement is true in the light of the data we have collected. Another way of looking at it is as follows. We have estimated beta 2 to B2 to be 0.029 about. That is obviously not 0. But we also know that this is an estimate. So that doesn't mean that beta 2 is this value. So the question we're asking is the following. Is it possible that the true value of beta 2 is indeed 0, but our estimate came up to be non-zero? Well, to answer that question, we really need to figure out how far this estimate is from 0. And unfortunately, we can't just look at this number and say 0.029 is far or not far from 0, because that's sort of relative. So instead, we have to do it in relationship to the standard error, the precision of the estimate. So for this reason, we calculate a t-value for the statistic, and the t-value is precisely the ratio of these two. The B2 divided by the standard error of B2. And if this is large in absolute value, then B2 is far from 0, and we should reject the null. So just in general, to describe this for an arbitrary beta j equal to 0, we define a t-value tj, which is bj over standard error of bj. So we're going to call this the t-value or the t-statistic for the particular variable. So t2, if we put a 2 here, this t2 is the t-value for SATV. The t-values are always computed by econometric software. So this is precisely the ratio of this to this. So SATV has a t-value of 2, SATM a t-value of 4 something, and GPA a t-value of 1.7 something. So what allows us to actually do hypothesis testing and figure out critical values and when to reject the null hypothesis is this result. We can show that if the null hypothesis is true, that is, if beta 2 is true, then this t-statistic, the t-value, will follow a t-distribution with n minus k degrees of freedom. Remember that k was the number of beta parameters, and k is one more than the number of explanatory variables. So in our example, k is 4. Note the consistency with what we said about hypothesis testing when we had one explanatory variable. Then the t-statistic followed a t-distribution with n minus 2 degrees of freedom. And that makes sense because with one explanatory variable and an intercept, k is 2. So this is just a generalization of that result. So knowing that the t-statistic follows a t-distribution under the null, all we have to do is to check if our particular t-value is in the tail of the t-distribution. If it's way out in the tail of the t-distribution, it's much more likely that the t-value is not drawn from a t-distribution, and that in turn means that we have to reject the null hypothesis. So here's the procedure for the test. First, we have to agree on a level of significance alpha. That was the probability of incorrectly rejecting the null. So if we agree on alpha equal to 0.05, we accept that whenever we claim that the null hypothesis is false, there is about a 5% probability that we're actually making this claim in error. Once we have determined a level of significance, we can find a critical value which determines if we are in the tail of the distribution or not, and the critical value is then t alpha half because we have two tails, and n minus k because that is the number of that is the degrees of freedom for our t-statistic. So if our t-value after removing a possible minus sign is greater than this critical value, then we're in the tail and we should reject the null. If this doesn't happen, then we say that we do not reject the null. But if we do, we also say that bj is statistically significant, or statistically significant, I meant to say, or significantly different from 0. Alternatively, meaning the same thing, we say that xj has a statistically significant effect on y. So looking again at our example, if we agree on 5% as our level of significance, we can find the critical value. Here, tools, statistic tables, t-distribution, the degrees of freedom. Well, we have n is 99, k is 4, just count the number of rows here. So we have 95 degrees of freedom, and this wants just the right tail probability. And the right tail probability is the same as the left tail probability, half of the total probability. So 0.025, alpha divided by 2. The critical value is 1.99 approximately. So if we look at the t-values, we see that this is greater than 1.99. So the null hypothesis beta 2 equal to 0 should be rejected. And we can say that this is statistically significant, and we can say that it's significantly different from 0 at the 5% level. And we can say that the SATV score has a significant effect on the expected result on the final. Again, with a level of significance equal to 5%. Whenever we're making all these claims, there is a 5% probability that we are doing that incorrectly. We can see that this too is greater than the critical value. So the same thing can be said about the SATM. While the high school GPA is not. This is not greater than the critical value. So we cannot reject the null hypothesis that beta 4 is 0. That does not mean that we can conclude that beta 4 is 0. We cannot make that conclusion. Remember, we never accept a null hypothesis. All we can say is that in our sample and with our alpha, we are unable to show that GPA has a significant effect on the expected final. That also means that even though our estimated beta 4, our B4 was 0.37, what we're saying is that that could just be a random fluke. And it's not a completely unrealistic value to observe given the high standard error. So the statistically significant effect corresponds to a statistically insignificant effect if we cannot reject the null, such as was the case for the GPA. B4 is statistically insignificant or insignificantly different from 0. GPA has an insignificant effect on the final exam. Now, this is all fine and well. The only sort of a little bit of a problem with this is that we have to go and find the critical value and compare that to the t ratio. And it's not really possible for statistical software to print the critical value because that depends on the level of significance, the alpha, and Gretel doesn't really know which alpha you prefer. Well, I guess they could have printed the t-value for alpha, the critical value for alpha 5% because it's so common. But it turns out to be really completely unnecessary once we introduce the p-values. So just similarly to the case when we had one explanatory variable, the p-value for an hypothesis, such as this one, is defined as the level of significance when you are indifferent between rejecting and not rejecting. That is, it's the level of significance that makes your t-value exactly equal to the critical value for that particular level of significance. Remember, the t-value is calculated from the data, and that means that I can always search for a value p here, which makes this equality hold. If the left-hand side is smaller than the right-hand side, then all I need to do is to take p down, because then that will increase the critical value. And because we have this exact relationship between the critical value and the level of significance, which is inverse, we know that we should reject the null if this p-value that we can calculate is less than the level of significance that we decide on. And vice versa, we should not reject it if it's greater. So looking at the example again, it's just so much quicker looking at the p-values. If we decide on p equal to 0.05, we immediately see that this is less than 0.05, so that should be rejected. We reject beta 2 equal to 0. This is way less than 0.05, so we reject that beta 3 is 0, while this is greater than 0.05, so we cannot reject that beta 4 is 0. A nice way of remembering this is this we talked about before. If p is low, the null must go, and that is of course in relationship to alpha. If p is less than alpha, reject the null, otherwise don't. Finally, the large n discussion, we touched upon that previously. If n is large, everything we've done so far works okay, in the sense that the p value we calculate, which is based on the assumption that the errors follow a normal, will be very close to the true p-values, which will be slightly different if the error term does not follow a normal distribution, at least if n is large. But such an approximative argument cannot be made for the other two assumptions. If the error term is correlated with the one of the explanatory variables, or if the errors are heteroscedastic, then we really shouldn't trust these p-values. So we have spent a lot of time talking about this particular null hypothesis, that is beta 2 is exactly equal to 0. That makes sense because it's by far the most common type of hypothesis we test in econometrics. But there are actually cases when we want to test something else, such as maybe beta 2 equal to 1 perhaps. Maybe beta 2 is a measure of elasticity and we want to test if, for example, this is a demand function, whether demand is unit elastic or not. So it is possible sometimes we do have something different from 0 on the right hand side. To test this hypothesis, you basically use the same strategy. You find a test statistics and a test statistic and a critical value, and you find a p-value and you reject it if the p is low. It's just that you can leave all the details to the econometric software. Just as an example, let's say I want to test if beta 4 is 1. Yes, I know that doesn't really make too much sense. I am testing if 1 unit increase in GPA corresponds to 1 more point on the final exam on average. In Gretel, you can carry out this by going to Test and go to Linear Restrictions. Then you can just simply type in the restriction you want to test. And in Gretel, you do it in the following way. B parenthesis should be this type of parenthesis. Then type the name of the variable, HSGPA, and parenthesis, and then equal to 1. So this is what you need to type if you want to test beta 4 equal to 1. Once you click OK, Gretel will give you a p-value. It's right there. So this null hypothesis should be rejected, at least at the 5% level. In eViews, you can do the same thing by going to View, Coefficient Diagnostics, and you go to the wall test. Sometimes this is called a wall test. There is an example to follow below, and in eViews it wants C instead of B, and it wants a parenthesis and not the name of the variable but the order instead. So if I want to test GPA, I have to check that that's the fourth one in order. So I type C of 4 equal to 1, click OK. Here's the t value of the test, and here is the p value. You can also test hypotheses that involves more than one parameter. As long as you have only one restriction, it's still going to be a t-test. So you might want to test an hypothesis such as beta 2 plus beta 3 equal to 1. For example, let's say you've estimated a Cobb-Douglas production function, then this test could be translated into the fact that the production function has constant returns to scale. But there are many other cases where you want to test a restriction that involves more than one of the parameters. One hypothesis you could test, for example, in this case, is if 1 point on the SAT verbal section has the same effect as 1 point on the math section. That is, we can test if beta 2 is equal to beta 3. So that would mean we want to test beta 2 equal to beta 3, which is of course the same thing as beta 2 minus beta 3 equal to 0. eViews, just go to View, Efficient diagnostics, wall test, C1, 2, and 3. So C of 2 is equal to C of 3. We get a p-value of 0.16. So we cannot reject this null hypothesis. It's actually possible that the verbal and the math section have the same effect on the final result. And in Gretel, finally, you would do something similar. You would do test, linear restriction, and you would write B. Oh, let's change this first. SATV equal to B SATM. We get the p-value. Actually, that gave us an error. Gretel doesn't like this formulation with an equal sign and the parameters on both sides. It basically wants the hypothesis formulated in this way. So if we reformulate it as this equal to 0, it should work better. Then we get a p-value of 0.16, which is exactly what we got in eViews as well.